Lecture 2 covers sections 2.1 through 2.2. At the end of today's lecture, you should be able to describe a force vector in terms of its magnitude and its direction. You should also be able to calculate the magnitude of 2 and 3-dimensional vectors given the constitutive x and y, or y and z, or x and z components for 2D vectors, or the x, y, and z components of 3D vectors. And you should be able to identify the 4 main types of force vectors: concurrent, non-concurrent, parallel, and collinear, as well as the subtype of parallel force vectors, i.e. distributed loads in 2 and 3 dimensions. For us to begin, we have to talk about a force, and we need to know the difference between the variables that we define within this course. Scalar quantities are things such as length, speed, mass, and time, and these are described by a single real number. And when we talk about scalar quantities, the variable is going to be italicized. That is, length is italic L, speed is italic V, mass is italic M, and time is italic T. Now when we talk about vector quantities such as velocity, displacement, force, or acceleration, these quantities are described by both a magnitude and a direction. And when we denote these variables, for instance, velocity is going to be a boldface V, or it's going to be italic V with a vector over top. Now when we talk about a force, first and foremost it's described by a scalar value which denotes its magnitude. In the figure shown below, we have a 10 kilonewton force. Now, knowing its scalar value is not enough. We also have to know its direction, which it's described in relation to the principal axes. That is, this force is acting 45 degrees above our x-axis, as well as our point of origination or termination. This vector is starting or originating at the origin. And we have to determine its point of application, i.e. is it on the surface of a body, in which we call it a surface force, or is this force arising through some type of field, either a gravitational or electromagnetic, where it's going to act at the center of the mass of the body, and in which case we'd call it a body force. Now, to best describe a force, we need to define a coordinate system. And our primary coordinate system is going to be a rectangular coordinate system, where our axes are mutually orthogonal. And this is known as a Cartesian coordinate system. Now, within the Cartesian coordinate system, we have unit vectors that describe our x, y, and z components of a vector, as well as our coordinate system. Now, a unit vector has a length, i.e. a magnitude, of unity. That is, a unit vector has a magnitude of 1. Sometimes a unit vector is called a direction vector. Now, we have an infinite number of unit vectors that can describe an infinite number of force vectors. However, there are 3 unique unit vectors that comprise our Cartesian coordinate system that we will use to describe any vector that lies within. In 3 dimensions, our first unit vector is I hat. It's an I, as opposed to with a dot, it has a caret over top. And this is our unit vector in the x direction, as shown by the blue arrow in the figure to our right. I hat is described as 1, 0, 0. That is, it has a length of unity in the x direction and has no y or z components. J hat is the unit vector in our y direction. It is given as 0, 1, 0, where there's no component in the x or z direction, and it has a length of unity in the y direction. Lastly, k hat is the unit vector in the z direction, given as 0, 0, 1, and this is shown as the green vector in the figure above. We have a length of 1 in the z direction, and no other length contributions in our x or y directions. These 3 unit vectors are mutually orthogonal, and they comprise our Cartesian coordinate system. Now, within a 3-dimensional rectangular system, we can now express our force vector in terms of its x, y, and z components. For instance, if we have a general force vector, as denoted by the blue arrow below, F is going to be equal to F sub x plus F sub y plus F sub z, where F sub x is the contribution of our force vector existing in the x direction. F sub y is the contribution of our force vector acting in the y direction, and F sub z is the contribution of our force vector acting in the z direction. Now, since our vector has both magnitude and direction, we can re-express it as F sub x I hat plus F sub y j hat plus F sub z k hat, where F sub x, F sub y, and F sub z, without the vectors over top, indicate the scalar value, i.e. the magnitude of the x, y, and z components respectively. The I hat, j hat, and k hat provide the directionality. Let us look at an example. Given the following vectors, we want to determine the magnitude of our x, y, and z components. In our first situation, we have a force vector given as 4.2 I hat plus 3.8 j hat plus 5.3 k hat. The magnitude of our force vector in the x direction is 4.2. The magnitude of our force vector in the y direction is 3.8. The magnitude of our force vector in the z direction is 5.3. Now let's look at a slightly different representation. Note we can represent a force vector either as a boldface variable or an italic variable with the vector arrow over top. And we can use our I hat, j hat, and k hat unit vectors to describe the direction, or we can put our vector within our angle brackets. So in situation 2, we have a force vector described as 8, 3, 4.2. So the magnitude of our force vector in the x direction is 8, that in the y direction is 3, and that in the z direction is 4.2.